welcome to the crypto course. So I'm Syed. I'm also a researcher at Web3 Foundation. Beside that, I will start the intro. Look at this. So this equation, I hope you have seen and familiar with it. It is in inner product argument, zero knowledge proof system. I think it's bulletproof. You don't need to know this stuff, okay? That is a joke. But actually, in the last day, we look at this equation at least. So also you learn something, but this is on top of here. Our goal here is to abstract this part out and show you more of a concept of cryptography with touching math as less as possible. Though sometimes you need to look at some of the math, but the math shouldn't be more than high school, basically level math, not like this. Okay, so I'm focusing for this lesson, which is intro to crypto, and I'm telling you what I hope you get from this lesson. So the first part is we just see what actually cryptography wants to achieve. What are the goals? Then we talk a little bit about the assumption that we have. How is our network? What we can assume? What we assume that the adversary knows, and what does it know? Then, from the goals that we start and assumption we have, we talk about which kind of these goals that we said, like which one of them the cryptography is going to protect for us. And then, which probably most part of the lecture is I'm going very fast over these primitives. So primitives is the word we use in cryptography. It's like a toolbox, right? So when you're a cryptographer, you have a toolbox, and then you have tools for different action that you want that gives you some of these goals. So the rest of the lecture, we go very fast over like the category of this primitive. So we are not going to do into like a specific implementation of these primitives. But we are going to familiarize ourselves with these tools. That's here, and then in the next lecture from today afternoon, tomorrow, and the last day, you go more deeply in each primitive, that how does it work and how it's being employed. So before talking about the resources and goals, I just give you this picture. It's like a high-level picture of what is a subjective way of we divide cryptographies. Maybe somebody else sees a different way, but from the way that we are using it, probably that makes sense to us. And so you have this picture in your mind for this course, for this module. Then you see where we are touching at every lesson. So we could divide the cryptography function in three big modules. And one of them are the symmetric cryptography, the thing that people think about when you talk to them before you see what is inside the actual crypto. The second category is the one-way functions, is the most complicated one and has the most rich set of tools. And the proof category, which we touched at the last day. And the one-way function, we divided in both big category, asymmetric cryptography and hashing. Oh, sorry. I'll learn to keep it close to my mouth. During this course, we are going to talk about each of these categories, but today also I'm going over I'm not touching the proof today, but I will touch over all this category from symmetric and one-way function and the subcategory of asymmetric. Anytime you have a question, I think it's okay if you interrupt me, because at least today we have a good time for this course. We have enough time, so we are not rushed. Okay. So first, so just our assumption. So we make this assumption and we stick to them for the rest of the course, and then we don't design systems that don't uphold with this assumption. The first, the major assumption we make that internet is a public space. We are not going to trust our ISP. We are not going to trust our Wi-Fi network here. We are not going to trust any intermediary system as for being secure or trusting them, like a sysadmin, for example. As a result, when you use the internet, the adversary is always there, it's public, and this public adversary who has access to this equipment can read all your messages. So you send a packet, they will read all the detail. They can impersonate others, and they can tamper with your message. So a good example for that are emails. So emails are basically, they are designed for the era before cryptography became popular. And you can do all this thing with the email that is not encrypted or signed. So if you don't send your email over TLS, which is not a requirement for the SMTP server to send the email, then everybody on the internet can read your email till it reaches the person. And even if you send it to TLS, the server that get your email, they can open and read it. And as you see, there's no guarantee for the from address that you have any possession for it. It's just part of the RFC of an email that anybody can write any from in it. So they can impersonate your boss and say, like, send this much money to somebody else. And actually, you don't have access to your boss' inbox, but they can put the email on the from. There's no protection against that. And the other thing is, if somebody asks you, like, give me $100, and then they can tamper it and make it $10,000. So they also can change the message, because there's no protection against the message. So the protocol was basically designed without any cryptographic protection. So that is what our adversaries are able to do. So in our network, we don't have any of this protection by the network. We have to implement it with cryptography. Some more resource. So one thing here is that, so we assume some constraint on resources. So for example, we want to work on a large data. We don't want to exchange it every time. I can tell you that to make sure that you have the same data as I have, I'm going to send the whole data to you every morning. I don't have that resources, but still I need some guarantees that when I say we are working on the shared data, we can easily say, oh, we are working on the same data. But for privacy, we even have a bigger assumption. So the assumption is that the private channels are very constrained, but in real life, they don't exist. So the private channel, if you don't trust the internet itself, then basically you have to meet each other in person, which in this world is not something practical if you ask all the users to do that. So for the matter of our practical application, private channel don't exist. Okay. And this lack of privacy, we also apply it to our protocol and to our code. So a fundamental principle of cryptography is a Kirchhoff principle that says if you want to assume that something is secret, it's just the information, a piece of information that you can assume is secret. You cannot assume that your method is secret. So I can't come and say, I'm going to make some cryptography protocol, and I'm not going to tell it to anybody else. And because they don't know how does it work, they just see gibberish, and then they cannot break the system. So this has been failed many times. For example, the protection for the DRM for the DVDs was a specific protocol, and they wouldn't give it to you unless you sign an NDA that you're not going to tell it anybody else, and then you could implement it in your video player. But if it was open source video player, then you were not able to do it because then it would be open. So it's completely against this principle. Yes, the security was based on the fact that you're being closed source, and eventually people reverse engineered it, and now there are open libraries that can play DVDs. So you don't want to put your trust and your wallet and everything else, on something that you hope people won't be able to find. So the only thing you can say, I'm hiding this 30 byte, 40 byte, and that's all my system. After that is open. They see all my code, and without having that bytes of data, they should not be able to break. That is coercion. So in this assumption, what does cryptography in this kind of world that everything is open, what kind of a guarantee cryptography is going to bring for us? So the first one is what everybody. Oh, sorry. Okay. Yeah. Sure. Can you say your name also?
Yeah, my name is Gunjan. I want to ask, what is it about computationally not feasible to break? So what about reliability on the computation power needed?
Yeah, good question. So the question is, so I'm going back here to the resource. What about assumption on the computation? So these were the assumption I talk is assumption of us as a user, not the adversary here. We do make assumption on the adversary to have a limited computational power. The exact assumption is probably, in general, we assume that the adversary cannot run asymptotic non-polynomial time algorithm. But we could also make a hard thing that says, okay, they don't have a computer that's can run this many instance of something. But in general, we assume a limitation on the adversary of computational power of adversary. We don't, in that sense, we don't have that kind of computational constraint on us. But still, there are some computation that we want to limit at the side of the users. For example, in the case of proofs, you have some limiting computation. So you can generate some proofs, but maybe it takes 1 year, and that is not feasible for us. So this is what the slide is talk about. But also, we make assumption on the adversary. We will get to that in more concrete way on some system that what assumption we have that adversary doesn't have power. And eventually this assumption fails when the years pass, right? So their computer become faster, and then we have to change our system. So and like quantum computers will totally change but we make another assumption, like we say they don't, yeah. So our assumption, even the computational assumption, is based on the algorithm that currently exists. But there could be other algorithm that nobody have thought about it right now, but they can come with it and basically make it easier. So there are some computational assumptions that we do that they are not proven, right, on the adversary. But I will get back to more detail on that when I talk about primitives.
Okay, thank you.
You're welcome. Okay, back to this. So the first thing we assume, when we tell people, say I'm a cryptographer or I work on cryptography, the first thing comes to people's mind is data confidentiality. So that's basically if a lay person will expect from cryptography is confidentiality. That I have a data, I send it to somebody else, or I leave it somewhere on the internet on the storage, and I don't want anybody else to be able to read it. So that's basic confidentiality. The only person who is intended to should be able to read the data, and people that I don't want them to read, they should not be able to do it.
Can I ask a question
Yes,
about that?
sure.
So I'm Mario, by the way,
Thanks.
one of the 3 Marios in the room. um, you talked a lot about security, and now I see the same thing. You talk about data confidentially. Does that for you mean that within the crypto world, cryptographic world, you cannot hack it? So you cannot tamper a message? Is that what you're saying?
So data confidentiality is not talking about that, right? So
well, when you tamper a message, it's also about...
there is another properties, but that was that we talk about the thing. So I'll get to that. So that is another guarantee that we want to uphold, that we want to stop the adversary from tampering the data. So in the field of cryptography, so we are talking about the math behind this thing, and then people are going to implement it. So there's another level. What cryptography wants to do is to make some assumption, like the assumption that, I forgot your name, anyway, you then said, is that I have some assumption. The adversary doesn't have this much power, this algorithm don't exist to solve this kind of problem, this problem have been hard. People 100 years couldn't find it. So I assume these assumptions, which are pretty hard assumptions, like they're tested over the years. And based on those assumptions, then I can show you mathematically that if they cannot break this algorithm that hasn't been broken for 100 years, then they are not be able to tamper with data without you knowing it, okay? Now, in the implementation, there could be a lot of mistake. So this is the mathematical part of it, but then you go to implement it, and then, or you use your key badly, or you violate some of the assumption about like the randomness that I had. Like for example, I say if I have a fully random key, then this assumption holds. And then you go and you put your birthday as a password, then some of the assumption fails, and then you can break those guarantees. But then mathematically I come back and I say I told you if this assumption holds and you violated this assumption. Or your coder went and coded something that's leaked information because of the timing attack, for example, which is not addressed here. So the implementation of the guarantees are not addressed here, but the theory of the guarantees, as long as the principle holds, these guarantees should hold mathematically.
Or the 51% attack.
So for example, 51% attack is assumption. I say 50%, 51. I assume that 51%, or on like other blockchain, like 2/3 of the validator, for example, 66% of the participants are honest. If that fail, then I have nothing to tell you, because the assumption has been violated. Okay. So data confidentiality is the first thing that people assume from the cryptography. The other one is data authenticity. And this basically covers the fact that if you there's a question. Yes.
So my name is Albert. So on top of what the gentleman asked about, and you also mentioned about the quantum computer.
Yes.
So I saw in the note that there is a risk because quantum computer violates some of the assumptions that you mentioned. Even AI, because some of the mathematical model, I saw last week that AI solved a mathematical problem that no one can solve in many years. So I just want to get an assessment, because in the note it mentioned that there will be development in, for example, Polkadot or other POS blockchain that they are going to catch up. So that even if there's a risk, then it's okay. But it's sort of vaguely mentioned that it should be okay. I just want to get your taste or your thought about how big is this risk, because it seems like things are moving much faster now with AI, even quantum computing. So if the foundation is, or the assumption is invalid, I would think it means the whole base of the blockchain actually becomes not valid anymore. So does it mean that all the Bitcoin, all the Ethereum, Polkadot will be dead by then, or what's your thought?
Okay. So so this is a lot of philosophical question, right? But first I'm addressing AI. So AI is not strong in creativity, and any like exciting attack that has come out in recent year has been out of creativity. Like you need a creative algorithm. AI itself is very computational intensive. So I personally don't think AI can invent a new attack that we were not able to do it, because the type of attack is not a type that with more computational power or with like more neural network with machine learning can you get to the new attack in this way. Quantum computers are not like that. We exactly know the algorithm to solve some of these problems. The symmetric crypto is mostly immune, but the mathematical problem in asymmetric cryptography, we know about them that there's algorithm to solve it. There hasn't been any quantum computer to the level that can handle that much computation yet. But if we know that exists, but also there's other algorithm that the quantum computer, nobody knows how. Like there hasn't been an algorithm for quantum computer to solve them. No, let me finish and I give it to you, okay? So we know the algorithm, they are much more expensive, right? So we don't want to use them right now because it makes the network very slow. Your cryptography becomes so slow that you don't want to do it. But at the moment you see that the quantum computer power is catching to that, you can change the underlying cryptography and move to that. So there is a concrete solution for solving that problem. But in theory, if one of these, like these curves that we are using and we haven't found the solution for it, overnight somebody finds the solution to the problem is much faster, in theory break, but probably they won't tell you. They're just tell NSA. I don't know. But also it's very unlikely to be found because so many years that nobody had found it. Like elliptic curve cryptography was introduced in before 80s, like beginning of 80s. And then nobody used it for 25 years because everybody thought maybe some mathematician come and find a solution. But after so many years, all the solution was worse than just searching for the key, then people trusted and now they're using it. So yeah, I can talk more about this, but let's move on. Yeah, I think these people are first and then.
All right, so
introduce you.
Yeah, my name is Marcus. I guess my sort of like statement is more or less two-pronged. In response to him and more or less a question back to you. But just real quick on the response real quick. So in regards to the quantum computational devices being able to crack cryptographic problems, more or less. A lot of institutions, I believe it's the NIST, I believe, are coming up with algorithmic solutions in regards to handling qubits and everything else, basically more or less using those as a way of a cryptographic quantum algorithm, more or less. So we be able to definitely more or less integrate that into your blockchains in the future if we ever get to a point where quantum computing becomes mainstream, more or less. And the second problem here for a sort of like question that it more or less ties into that response. Have you ever talked with anyone in regards to using quantum cryptography for Web3 solutions before? Or at least read any sort of like papers?
I didn't get the question, sorry.
Using quantum cryptography for Web3 solutions, more or less.
Have anybody has used it? That's
Or at
the
least,
question?
well, more or less, has they read any sort of papers on it, or has he sort of
Yeah, of course there is. I saw, like, personally, I saw like Ethereum wallets is quantum resistant and they were implemented.
Where?
That.
We have a professor coming on Friday, and her research is in quantum cryptography, I think.
Oh, nice.
We can ask.
Yeah, I definitely want to talk with her then. All right, sounds good.
Let's do these two more questions and then we move on. Is there, or the question has passed? If not, then we give it to, I forgot your name. Yeah, I do. I guess.
Mike.
Oh.
Be careful.
Okay, that's the last question. We move on from this subject.
You can toss it.
I'm just gonna
put a video about what I was gonna say on Discord, and then
Bring it closer to your face.
whatever I was gonna say, I'm just gonna put a video summarizing it in Discord so people can see it. But basically, it's about Shor's algorithm and quantum cryptography and a quantum solution for the problem faced by quantum computers being able to solve the algorithm.
Thank you very much. Okay. So we'll touch base on this issue a few times later when we talk about the algorithm, and then yeah, the last day we have the professor whose research is on that, and hopefully they will teach you about that. But here, so the next goal I want to guarantee is data authenticity, and that's what does it mean? It means that when I receive a data and I'm sure the origin of the data is correct. So I receive an email from you. I know it is from you. So nobody has the person who says he wrote the data. They are the author of the data. Related to that is data integrity. So the integrity says the data I received completely was what's sent, and nobody had tampered on the way in the data. So I get the data, maybe it's my data, like that is the difference between authenticity and integrity. So I know it's my data, I put it somewhere, I went and take it up, get it back, I want to be sure that what I put on the cloud is the same thing that I got back. Cryptography can help us with this. And then the last one, which is mouthful, non-repudiation, is related to the data authenticity, but it's a bit from different perspectives. So when you send me an email and I receive it from you, then I should be able to prove to the other people. Now I received it from you, but I should be able to prove to other people that I got it from you. So you cannot deny that you have sent it. So it was obvious for me that I got it from you, but I should be able to tell other, like, to uphold it to everybody else. And something that we don't deal with cryptography, and we hope that there's other algorithm that does that. So it's not part of the cryptography, but a lot of mathematics has gone into it, is data availability. So cryptography doesn't say, oh, you always can have access to your data. They say if the data is available, then is intact, and I tell you who sent it, and then the person's like all this cryptographic guarantee on it. But if you get a DDoS attack and you don't get your data, then that's not the real aim of cryptography to defend. And there are other defense for this. You know, you have redundancy, you have erasure coding, which also we touch about this again on the last day. But just to know, this is not what actual cryptography doesn't deal with this part of the problem. But there's an example that, you know, also like if you write your, you know, is an example of area that's you need it for your, like for the blockchain, for example, to work, but it's not the area that cryptography touches on. Okay, so let's go fast over all this thing. So as I said, confidentiality is only people who know some secret from a specific secret that give access to the data should be able to have access to that information. And anybody who does not have that secret should not be able to touch it. So this is not very so this one I don't know how to use because it doesn't. So this is the basic definition of the confidentiality. I have the data, I have the key, I should be able to read it, and the person who doesn't have the key should not be able to read it. Simple. Okay, but there are like a cryptography system that gives a bit more fine-tuned guarantee on this, and these are this. So these are about like when, so I said if you have the key, you read the data, but now something will happen and is about the key compromise. So something happened and you lost your key, somebody stole your key and it wasn't encrypted, so they can read it, or they guessed your password and or your seed that was generating the key at some point. And there are other guarantees that cryptography can give you at this place. One of them is forward secrecy. And forward secrecy says, okay, you found Alice's key at some point, you stole it, you took it home, and now you're listening to the network conversation. You should not be able to guess, you should not be able to read the future conversation that Alice has. And then the other one is backward secrecy, is that, okay, you found Alice's key and you had stored all the conversation in like NSA facility in Utah, and then you should not be able to, using that key, to read all the conversation history before. So these are stronger assumption on data confidentiality.
Excuse me.
Yes.
Here.
Okay, sir. Okay.
So it seems if we implement one, we achieve other one automatically. So why do we have to
Forward and backward?
Yeah. So
No, it's not. So for example, what you can do here is you can hash your key, and then you every time you encrypt to that. For example, anyway, I shouldn't go into that in detail, but just for this, then what will happen is that the key, when you get a key, you can guess all the future key because you can apply that mathematical operation on that key. But that operation is one-way function, so you cannot go back to the backward key. So that will give you backward secrecy, but it doesn't give you future secrecy, forward secrecy, because they can do the same operation that you do to get the future. So you need to add randomness to get this one part, and you can use some kind of one-way function to get this part. But there is clearly two different operation needed for that.
Thanks.
Okay. Okay. Data authenticity. So that's as I said, is a credible expectation that you know about the origin of the message, where the message came from, who has written it. And it's basically make sure that the third party cannot pretend that they created some data without putting a trace that they have done it and fake the origin of the data. This is done by digital signatures mostly, and we are going to talk about it. So they are stuff that they're hard to forge, but they are easy to verify. Anyways, I will go more into detail into digital signature, and then we explain this with more detail. The last one, no, not the last one, but before non-repudiation. This one is basically you store data. You want make sure that the current state is the state that it was before created. So if somebody come and corrupt the data, you want to be able to detect that the data was corrupted or has been tampered. This is also done partially by digital signatures, and similar to physical signatures that we are using here. I sign a check and I give it to you, but this the physical signature are very, very weak in providing this. So for example, for physical signature, if you tamper with your certificate and change the year, the signature is still as valid as it was before. But we don't want that. We want that if something tampered here, make the signature invalid. And that's what digital signature will give us. Okay. The last property is this. So the difference with authenticity, as I said, is that you know that the origin is correct, but from non-repudiation, you don't want the origin be able to deny that they have sent something. This is important in a lot of application. You know, if you give me, if you tell me if you do A, Y, Z, and I give you this much money, and then I will do it, and then I say, look, this is a contract, and then they can deny that they had sent the contract. So that's about proving to the third party that somebody had sent the data to.
Hi, I'm Luca. How is that different from authentication? Because I assume both use asymmetric cryptography, and in both cases, I can lose my keys and someone can say, hey, someone else also has those keys.
Very good question. So, for example, you can use symmetric crypto for authentication, but not for non-repudiation. The difference is, for example, in symmetric crypto, you share a secret. And based on that secret, because I know only you have it, then when you send it to me and I trust you, that you haven't given the secret to somebody else, then I know that it's you. But if I want to go somewhere else and prove that you have sent it to me, I could have sent it the same thing because our secrets are the same. So.
But I can give that same key to someone else, and someone else can use the same key to send you the message. So you don't know if it came from me or it came from that other person.
I mean, that is a fundamental problem, right? If even in asymmetric cryptography, you share the key, then you don't know who has signed it. But so you can then your defense is that I gave it to somebody else. But here there is a problem that you say, maybe the system was designed that both of us share a key. And we can, based on that design, we still have authenticity. I know that data has come from this, but I have no way to prove to the third person about it. And there is this problem also, like is our secret key, I don't want to tell it to anybody else to check that is actually between one of us. It's not a system that's designed to reveal for the third party. Okay, so that is the summary of what we want from cryptography. And for the rest of the course, I'm going just skim over the primitives, the tools that we have to achieve these properties. And then the rest of the week, we are going to basically explain each of these primitive one by one in more depth and how we can actually program with it and use it in your code and stuff like that. So, okay, there's a question. Sorry.
Yeah, Boda here. So, like, just a quick question. Are we going later in the course to understand how to prove, like, the difference between authenticity and non-repudiation?
Yes, you will specifically see, like, how authenticity, like, the other ways is almost correct, like, always work. When you have a non-repudiation, you have authenticity. But you will see example of where you have the authenticity and it doesn't work for non-repudiation.
Thank you.
You're welcome. The order is a bit arbitrary here of the tools that we are going to talk, but we talk about, let's talk about the one-way functions. So one-way function, as you remember, if you remember in the first diagram, we divide them in two categories. That was hashing and asymmetric crypto. And they share this property that we call them one-way function. And these properties that the one-way function should satisfy is, the first one is it should be reasonably fast to compute in one way. And reasonably fast means very fast, like less than, like millisecond is not fast. So it should be faster than that, and easily some trivial operation with the computer that can compute that. On the other hand, if you want to reverse them, it should be very slow to undo. And here, when we say slow, is not It means very, very slow. Like slow is impossible. Like many years, or like the age of Earth or something should be taken to be able to compute the inverse. But mathematically it's possible, but it should be practically impossible. I should go down. No. Okay, it's next. Yeah. Okay, so the first type of the one-way function that we will talk about is the hash. Okay, there's a question. Sorry. Mike, and then also introduce yourself. Maybe for the first day is good. Everybody.
Regarding the previous slide here, I just want to make sure.
Okay, I'm going back.
So when we talk about reasonably fast in regards to some like O notation, for example, what are we talking about specifically? Are we something like faster than O log of n in regards to that, or anything faster? Is there any sort of like hashing algorithms are O of n even, or?
No, I mean we have to define what is n though. But if n is the size of your space of the keys, then Andrew's angry at me talking. But okay, I shouldn't talk much. But I won't go into detail. But yeah, I don't know. I think log n is also
It's
very
time. It just we're talking about time, not like actual algorithm.
Yeah, time complexity.
But we're not reasonably fast is meaning literal time,
Yeah.
not like mathematically defined algorithm complexity.
Gotcha. Okay.
Right. Say
I think so. I mean, you can define if all log n. It's not on my head, up top of my head, that this hashing algorithm are like how do they define, but also it depends how you define n. Is the size of the number of the bit or the size of the whole space? But it's more, yeah, we are more concerned about actual time here.
Gotcha.
Because you want to be fast for practical application. Then for the attack, you're more concerned into the algorithmic timing, because then you can make it big enough to become, as long as the asymptotically is very bad, then you can make it big enough that becoming possible in this with our computer to be broken.
Gotcha.
For computing it, you're much more concerned about time. So I can bring two algorithms that are basically the same if you do computer scientific or notation for them, but still make a big difference to choose one that's run faster.
Gotcha. Thank you.
You're welcome. Hash function. Yeah. So we are going to talk about this, but in short, is you have a large data and you don't want to deal with that large data because you don't have the resource, and you want to make a small representation of that large data, and that it's very similar to what like fingerprint does for us. So instead of like keeping all data of me to show who am I use just a fingerprint, which doesn't show who am I. The fingerprint doesn't say what is my name or something, but still uniquely identify who I am. So that's basically what we use hash function for. We use the data and we want a unique identifier that represents that data, even that it does not contain all the data. And they have a lot of application. For example, that one, like you use that in Git, for example. You represent a huge amount of data with one thing, and I say this set of data, and I just represent it with one hash, with a small fingerprint of that data. We use it for database access. So these are the hash maps, right? We cannot index the database with the data itself, and instead we make a small key out of the data, and then we can search that key in much faster time instead of searching the data. And then when we find the key, we know it's coming from that data, I can retrieve the data. Digital signatures, we are going to talk about this, but instead of signing the whole huge data, I'm going to sign a representation of that data, which should cryptographically bind me to the fact that I signed the data itself. Key derivation. we are going to talk about next lecture. But basically, you have one key. You want to get another key that is related to that key, but it's not the same. So, and pseudo-random function. So, you have some random data, and then you want to generate more random data from them, and hash function will help you to expand your random data. Okay. So now we jump to symmetric cryptography. There was another one-way function, which was the asymmetric cryptography. They're a bit more rich, so we'll deal with them at the end. But this one, let's go over this. So symmetric cryptography is called symmetric because all the algorithm in this area is start with a shared secret. So our knowledge of the secret is symmetric. You know the secret, I know the secret, and from that on we are going to use it to do my algorithm. The problem is with this is a very, very, very difficult requirement. As we said, we assume that there is no public channel, but we can eventually deal with this problem. But so for now, we can theoretically talk about symmetric cryptography, but we have to solve this problem because that doesn't fit our model. We cannot share secrets basically on the internet. We don't have a private channel. But suppose we share the secret, and now we are going to use this secret to protect our communication. Protect in the sense of confidentiality and also somehow about authenticity and integrity. An easy way of thinking about this is that I had a very small secret that we shared with each other, and now we are extending our secret. When I make a more secret between us. So we shared a very small secret, we have shared the small data, and then I'm extending it to get more and more and more secret data between us because they look the same. The activity that we do this afternoon is somehow touching to this property of the symmetric cryptography. There's a question, sorry. And your name.
Okay, would you mind to
introduce?
The second one, this is a potential very difficult requirement. Would you mind to explain it more because I didn't get it. What is?
Okay, sure. How me and you? So one of our resource constraint was that private channels are very, very expensive and basically don't exist. So I assume me and you, we have no way of having a private channel. The only thing we have is internet, and internet is completely public. Any communication between me and you is public. So the problem here is that how can I share secrets with you when I don't have any private channel? So anything I'm sending on this channel has been seen with everybody else on the internet. How can I share this secret with you? So so we have to find this mathematical solution to generate private channel that doesn't by default exist. There's another one. Mike, and introduce yourself.
Could you, Luca again, could you use something like a key exchange? So even if it's a public channel, like you still have mathematical properties that guarantee that only the people on the end actually have the same key?
Sure, yeah. So that's what basically I was referring to. So we have a mathematical solution to this problem to generate this private channel that by default doesn't exist. So that key exchange is the mathematical solution to this problem. We get to it eventually. More questions, sorry.
So,
Introduce yourself.
Yeah, hello, I'm John. So what does the last sentence mean? Extending a shared secret, can you elaborate
Over
on
time,
that?
yeah, sure, sorry, maybe I wasn't clear enough. But so I come to you in person, this is my private channel, and I say, let's agree on one word, like Polkadot Academy. And that will be our shared secret. Then this symmetric cryptography, it helps me to use that shared secret to generate more secret between us. Like I can encrypt a book and all become gibberish, and I can send it on the internet to you, and you receive it, and now you have this book, you have all the content, and I have it too. But nobody else on the internet saw it because I applied symmetric cryptography to it. So now our secret was only Polkadot Academy because we saw each other and I had only time to tell you the secret, but now I extend it to a book. So I have a book that I only know about it and you only know about it.
Sorry, so does it mean like you can derive more symmetric keys based on the video fusion one we share?
That also makes
rotated by time, right? So it's like
that also could makes that also, but there's another way of extending it, right? So in that way, I didn't need to send the data to you. But another way of saying is that because I encrypted the data, I was allowed to send it to you, and then in both sense, okay. In both sense, these two. Just a second. In both sense, these two. I mean, they don't increase the entropy from the beginning. There's another question here. Yeah. But you need a mic.
We're coming. It's coming.
1, 2, 3, do it.
1, 2, 3, go.
Go. You can do it.
Okay, so let's not do that.
Don't send it up, guys.
Pass it to multiple people. Pass it, oh my God.
Pass it down now.
By the last day, you will be good at it.
Does it work?
I hope it.
No,
Exactly.
The key is to toss it to 2 people in between.
Yeah, actually. But yeah, Marcus again. It's more of an actual just my understanding, basically, more or less, of the material here. Just if anyone needs more clarification, it's systematic cryptography, from my understanding, is kind of like those cipher wheels that you used to have as a kid, basically, where the shared secret is let's say y=5, for example, then all the other letters are more or less aligned to each of the actual numbers, more or less. So if you can be able to encrypt a message more or less using that cipher wheel, more or less, let's say on y=5, then if you tell the party, hey, y=5 for the wheel, they would be able to decrypt the message, more or less. Would that be the correct interpretation of what systematic cryptography is?
Yeah, sure. It's an instance of it. Yeah. Now we use more complicated algorithm, but essentially is that's it. You get a key and you use mathematical operation to extend your secret and use that to encrypt your data. But essentially that is what comes to people when they think about cryptography. So that's the symmetric cryptography. Yeah.
Yeah.
And I think somebody has a question.
Yeah, Alvin here. So I'd just like to know, is asymmetric encryption kind of safer or better than symmetric encryption?
I will get to that, but it also depends on definition of safer and better. You need some property it gives the asymmetric encryption gives to you, but symmetric doesn't. And when you talk about safer, it's very depends on the size of the key. So if you enforce that you have the same size of the key, then no symmetric encryption is safer, I guess. But that is not how we work. What is very clear is that symmetric encryption is much faster. And most of the symmetric solution right now, they are quantum resistant, but most asymmetric solution that we are using are not because they're more costly to make them quantum resistant. So, but we should use it. We should use every tool for the purpose that it needs, and then when you have a purpose, then we use the best tool we have. So if our tool is to encrypt something, and both asymmetric and symmetric does it, then probably we are going to choose symmetric because it's faster and essentially more secure against quantum. Okay, so I'm going forward. So that's going back to what Mark said, for example. This was the most, this is the first modern system, symmetric encryption system that has been used the real world was Enigma. It was a machine, and you had what happened was that the parties in the World War II, the Germans, they had this booklet that had the keys, and every morning, so that was their shared secret, and every morning they would use a word from that book, and they would set up the machine based on that, and then they would encrypt the information. The machine was encrypting the information for them based on that, and then they would send it to the other party, assuming that the people in the middle cannot read it. The essential problem was that the algorithm wasn't doing a good job of extending the key. So the entropy of changing key once a day. So every day we are adding new entropy to the system. The new secret that comes the second day has no relationship to the encryption of the first day, but still it wasn't enough. So the allies were able to find a relationship between this extended secret and that original secret, and they would recover the secret from that, and then they were able to decrypt everything there. So it was an example of it which failed because the mathematics wasn't there, wasn't enough. Okay, so now we go back to the one-way function, the other category, which is asymmetric cryptography, and probably is the richest area of research in cryptography is here. Now here, why do we call it asymmetric? Because I have a secret, and then I apply some mathematical operation on it, and I get some representation of it, which preserves some property, but not enough to break the one-way function. So I have this representation of my key, which I transformed my key into it, and then we believe that with current mathematics that we know, with current algorithm that we know, and the mathematical and computational power that we have, we cannot use this property, this new identity to reverse it and get the secret out. And then I'm going to put this secret out for the world, the representation out for the world, and I ask them to do stuff to it. But I don't tell them the secret. That is why it's asymmetric, right? I have the secret, but outside they don't have the secret. That is how this name comes from. So there are some properties that you want it to hold, but the big property that you can reveal the secret from this specifically should not be possible. So then now everybody has the public key, and then they can use this public key, this representation, to perform mathematical operation that turn the data into encrypted form, such that the only person who can reveal the original data is the person who has the secret. So they themselves also cannot reverse this operation. And then that gives us asymmetric encryption. But asymmetric encryption is, asymmetric cryptography is much more than only encryption. So probably one of the most prominent use of asymmetric cryptography is digital signature. So again, we do the same operation had happened. I have the secret, and I send the identity that's generated from the secret to everybody. And now I have a unique way to prove that part of the information, to prove that I know this secret and associate it with some message, with some information. And that's basically what signature does. I say I had the secret and I approve this information. So that's how digital signature works. And as a result, when you can do that, you provide authenticity and integrity for the message, because now people knows that if you change the message, then the signature won't be valid anymore. It doesn't hold against the public key that everybody knows. Okay, and tomorrow we have two lessons dedicated to this. So hopefully we get very, very comfortable with digital signatures. But just now you need to know that this thing exists. They always involve a signing function. It get the secret, it get the message, and it speed up the signature. And the signature is in a way attached to this that nobody else can generate the signature, and everybody can verify that this signature was generated by the secret associated to that public key. And most importantly, you get a secret signature from me for some messages. It does not verify against any other messages. It should verify only in that message. If you put it in the verify function, it fails. If you put other so here also we get a non-repudiation, right? Because the signature will say only the person who had the secret was able to produce the signature, and for that I don't need to give the secret to anybody else. With the public key alone, the public information, you can verify that actually I generated this signature, and it should have been the person who had the secret that generated. So basically, as this point came out earlier, if the only defense I have here is that to say I lost my secret, somebody has stolen it, I haven't done it myself. But you cannot claim that this secret has not generated this signature. Okay, so just a fast review about this. So as we said about that question, symmetric cryptography is much faster. And is also is more resistant to quantum attack. But they need a trusted environment to share the secret. Asymmetric cryptography is slower and has, the assumption in it is much less strong. But it gives you all this, because of the mathematical structure, it gives you all other things that's the digital signature, the asymmetric encryption that doesn't need secret channel. It gives you all this good stuff, but it's not as fast as that. So basically, this will let us that in real life, we usually use always, if you look at everything, we are always using hybrid cryptography. And hybrid cryptography is to use many of these primitives together. So I know that symmetric crypto is faster and can give you confidentiality, even if, but it needs a secret channel. The hash function can help us to decrease the size of the data for representation of it. And asymmetric cryptography can dictate relationship between the participant. That symmetric cannot do that because it's just a shared secret. And using all together, then I can have a system that's take benefit of all this subpart and give me a better performance and better user experience. Okay, there's one more thing here. Is related to digital signature. Is about certification. And so the problem with the asymmetric encryption and digital signature that we talked is that I'm coming to you and I'm telling you that this is my identity. This is my public key, which is basically related to my identity, and then you can use it to send like an encrypted message to me, but there's a flaw here. How do you know this public key relates to me? It's just a mathematical random value. So to resolve that problem, they come, the subject of certification comes in play. And a certificate is a piece of data that is signed by somebody else. And this piece of data contains the public key that they want to make some claim about it. And then the information about who owned the public key and what they can do and what you expect from this public key to work. Is it for signature? Is it for encryption and stuff like that? And then there's some metadata that's until when this certificate is actually valid, and how, if it's becoming valid, how can you verify that it's invalid? So these are certificates, and usually they work like that. You trust some specific certificate authorities, like you're in your browsers. You have, when you download your browser, there's already some certificate authority inside it, and they can sign these attestation. And when you browse the websites, so this attestation, the good thing about this attestation is that they don't need to come from anybody specific. You can even find them like in a public registry. So, but typically when you visit the website, the certificate comes to you, and then you check if the certificate has been signed by one of those authorities that has been in your browser. And then if that, then you trust that the public key belongs to the website you're browsing, and then you can share a secret, you do key exchange and stuff like that. So certificate basically touches based on asymmetric encryption. There's a question. Sorry.
Yeah.
Okay.
Buddha here. So when we say it's signed, what do we mean exactly? Yeah.
Yeah, sure. Signature is a proof that I know the private key, and now I have to somehow attach it to the data that I'm signing. So the signing function basically takes the message. As you saw, it apply a hash function to it. It gets a representation from that message that you apply to any other message. You don't get that representation. And then generate a proof that I know my secret key, but the proof is attached to this representation as well. So when you want to verify it, you put the representation there and you put the public key and you get true. If you change the representation, you put your public key, it returns false. The mathematical equation doesn't hold, your proof doesn't pass. So it's a proof that I have the secret key, but the proof is also attached to the representation of message. So every time I'm signing a message, basically I'm proving that I know the secret key, but the proof attached to this representation of the message. Okay. So I think this is the last thing I want to go over, and again, this is attached to our activity today. We talked a lot about keys, secrets, like we have the secret, and then after that we have all these good protocols that does a lot of stuff to us. But the secret itself need to have some good property. If I have all this good algorithm, but the secret does not have those properties, then the assumption that we said they won't stand. So the notion of good secret and like even a good cipher, it comes from some information theoretic assumption. So we're going to talk a lot about entropy. Entropy is about amount of data that are non-redundant information in text. So for example, in an English text, you have a lot of redundant information because you use much more E than other letters, like there's not a lot of use of Z. So an English text is not a non-redundant data. A lot of data can be, like you can recode the English text to become much smaller. That is basically what the zip function does. So entropy is about a non-redundant information in a set of data. Randomness is basically knowing the data already, how much I can predict that what is the next bit that come. So it's about unpredictability of data, and it's very directly related to entropy. So when you have less entropy, then and you get less randomness from that data. We are going to talk about key in next lecture, and the key size is the upper limit for how much entropy you can have in that key. So if we talk all this about this algorithm and your key size is very small, then your entropy is very small, and then your system can break. The other way doesn't hold, right? So you can have a bad key even that you have given the levy to have a very, very good entropy, but then you're going to use a bad key. Your key has low entropy and can break fast. And there's a notion in theoretical cryptography called one-time pad. And one-time pad is an infinite string of random bits. And the cipher using that, so you have a data, you can XOR it every bit of your data with this infinite series of random bits, and you can basically prove theoretically that this cipher is unbreakable. The problem is that generating infinite size randomness is not an easy task to do. So, and if you don't have infinite size, then your cipher will break. And that is how our activity this afternoon is about, to break a cipher that uses a fake one-time pad and not a real one. Randomness. So randomness is a hard concept to exactly define. So here I can claim that I have written a dice, roll a dice function, and every time you call it, it returns 4.
Hi, here on your right.
I don't see you. Oh, it's here.
Yeah. So, hi, I'm Tushar. Can you please explain again the entropy thing? Like,
so entropy is a concept of the data. So I give
with some example, basically.
Like as I said, when I give you a file, then I zip it, the size becomes much smaller. But then I can completely recover the original file from that. So the amount of entropy in that file was much smaller than the size of the file. If the entropy is the amount of information that you cannot make it lower to be able to recover that amount after.
So is there a scale or something? Because in one-time pad you said like maximal entropy, so that can be different for different types of data, right? So is there a scale for this?
But it's infinite, no? So is there a scale for it?
Scale for entropy, like is there a scale?
Yeah. Can you compute entropy in some data? I think on top of my head, I don't know, but I feel like the definition is doesn't let you to have an algorithm that gives you exactly what is the entropy in the data. But in some cases, when I say like I have a key of 256 bits and I'm telling you you're allowed to change every bit whatever you want, then for sure when I say I chose something from that set, so there could be a set theoretic definition like that for the entropy.
It's like a definition, not a mathematical term or a
It has a mathematical definition. I don't think there's an algorithm that can give. Okay. You can get an algorithm from every set. You say what is the entropy of this set, because there is a lot of concept about how I can change the data in a way that I know the entropy fails.
Understood.
So, for example, you have 256-bit keys, and you're going to you have 256-bit entropy, but then I have some social concept that I only use English words for my password. So the entropy is much less, but I don't know if you have an algorithm to recover that. Like what is exactly? It's not 256 now bit. Entropy is less, but
it is comparable. But mathematical term is something that we don't use often, right?
We don't use the algorithm to compute it. Beside the fact that we know how much. So if I know how much randomness I have, then I can get exactly the entropy because they have this direct relationship. But the problem is the degree of non-randomness is not easy to define.
Right.
So for example, here. I can claim this is a dice, and you haven't seen, sorry, okay, go ahead, sorry. You need the mic. There's a mic there, mic. Okay, you did it. Okay.
Hi, I'm Tobias. My question was regarding the entropy as well. Basically, I wonder if on a computer system when everything is more or less deterministic, if we have good sources of entropy to generate keys and whatnot.
Next slide we talk about it.
Okay.
Good. So here again, if I can claim completely this is dice, but every time you bring a 4, so every time you call this function, even that you don't know the implementation, you make more and more assumption that probably is not actual dice. you have like you don't have 100% proof, but every time you get more proof that this dice is flawed. So back to your question, like you can make an assumption that it should have a 6 to power of time that you're rolling this dice. You should get 6 times more entropy every time you do, but it fails a lot of tests probabilistically. You can make an assumption that doesn't work. Again, to this question, in real life, how do we generate randomness? So we do pseudo-random sequences. These are complicated mathematical algorithms applied to some seed that generate sequences that look like random, but they are not actual random because they're pseudo-random, they're deterministic. But because it's very hard to recover the original data, we can treat them as random. Again, here you can argue that the whole sequence that I generated does not have an entropy because it generated from that key and deterministically has been generated from that key. But in real life, it's very hard to connect these two together. So if you have a good pseudo-random number generator, then we can treat it as new entropy added to the system. These are the real situations in which we use randomness in the computer. So if you check as /dev/u random, it gives you some real randomness from the operation that happened on the computer, and it comes, for example, from mouse movement, or like from the lower bit of your microphone noises, or from the keyboard sequences that you type up to then, or the CPU load and stuff like that. So you can gather them from the sources already on your machine, or you can use a special hardware to basically gather entropy from natural phenomena, like silicon gates and quantum amplifiers. There's a question, sorry.
Do we call them pseudo-random because they are not really random? Or why the name pseudo-random?
They are actually deterministic. So they are they run by, you run a mathematical function on it, and every time you run a mathematical function on that piece of data, you get exactly the same sequence. Yeah.
Another question.
This is Ryan. When someone does a trusted setup, are they just adding entropy basically?
Yeah. I mean that's part of it. So every time you add one step to that trusted setup, then you add one more factor that people need to guess to be able to break it. And our assumption is that 1% in trusted setup is trustworthy. Then the trusted setup is holding. It's basically the entropy of the trusted setup should be equal to the entropy of one key. That if we can guess that, then but in real life, if a more honest party, then our entropy is actually high because you have to guess all of them. Okay, time for summary. So what we saw here, so we saw that cryptography gives much more than encryption to us. Even when you talk to people about cryptography, they only think about confidentiality, but we saw it gives a lot other property for us. We talk about our assumption that the network we work on are public, they are all open, and we work on that assumption. We talk about access to information, which is reading access, which is confidentiality, or writing, which is the integrity and authenticity, which cryptography can help us to hold. It can help us to hold the expectation that a message is authentic from the author that we expect, and his integrity is untouched. We talked about a digital signature, which helps us to prove to other people that we know some knowledge without revealing our secret key. And we talk about hash function. which help us to represent big data succinctly. We're back here, and we touch base on this part of the graph, and we even talk about the hybrid cryptography. We haven't, these are the stuff we talked about in the last day. That's it for the intro, and if you have any question, I can. John is, now I remember your name.
So, can you go back to the slides on the certifications? Like, is there like at least 3 parties involved, or maybe 2 sets of keys, like a issuer, holder, and verifier kind of thing? Like
there is a 3-party involved, yeah. So there is a party that's trusted, which is the certificate authority. It can show up in a different way, and then there is a party that's required to be certified. So they bring their information to the authority, and then they sign it, and then the verifier is the 3rd party. So if you look at your browser, the authorities are different authority out there, like those that are selling the TLS certificate. The person that need to be certified is every website that has HTTPS protection, and verifier is the client that goes visit the website. It's not the only way of using certificate. So the other practical thing in the world is Web of Trust. That is some kind of a social certificate that I go and then I sign the keys of all my friends, and I say I personally went and saw this was John, and I know that he showed me that this is his key, so I'm going to sign it and put it out there, and John will do the same thing for me. And then I have 100 friends, I have signed all of their keys, and this is up in the internet. And then you come and you want to talk to somebody, you know he's my friend, and you see I have signed his key, and then you look and you see the 3 other common friends that you have also has signed it. So then you make a reasonable assumption that should be John and is not a random public key of an attacker in the internet, and you can trust it that way. So this is a Web of Trusts, and it was currently is implemented for GPG. If you look at the GPG keys, it retains all the signature on the key, and then GPG has a function to say, okay, upload my signature for John on the internet. So that is a bit of different system, but the certificate authority hierarchy is the most common one that is used in real world right now.
Thank you.
There's another question, 2 other questions here. You need a mic. There's coming from you.
Hello.
Hi.
So
Introduce.
you claim.
Introduce.
Yeah, you claim that.
No, your name.
My name is Gianluigi. You claim that digital signatures are composed by message plus a secret. So my assumption is.
It's not plus the secret. Yeah, it's a secret, blinded secret. But okay. Yeah. But just.
Okay. No, I mean my question was: is digital signature a form of hashing of a message that is when it's added as secret?
Yeah. So that's a good question. I mean, it's not a requirement, but then become mathematically impossible if you want to sign a 10 gigabyte data, then you have to sign every byte of it. What you do, you apply a hash to it, you get the representation. Almost all digital signature works like that. And then you get the representation, and then you add a blinded version of your secret to it, and then you blind them together, and then you get some value that mathematically can be verified that your secret has been used for that, and the hash, the verifier can compute the hash because there is a public function. So they are going to do that. They also are going to apply the hash, get the representation, use the mathematical protocol to verify the signature came from the same thing.
Okay. So my assumption is also that digital signature is not reversible, or it is.
It's not reversible. Yeah. That's part of what you get from it, and I think is also part of the definition. You get the signature, you cannot recover the message.
In terms of the differentiator between asymmetric and symmetric, you mentioned at the beginning that with symmetric there was a shared secret. What happens, and I'm trying to understand how this works, what happens if the secret's shared from the asymmetric part does it then become symmetric, or is this something that you decide at the outset and you can choose between the two?
I understand. So if I understand correctly, we have a secret. I have a secret, okay, as a party that I use it for my asymmetric crypto, and then I'm going to share it with you.
With multiple people, and then does it become as a status symmetric? Is that how it works, or does this go to how you're going to encrypt at the outset? I'm just conceptually.
Yeah, I understand. I don't think no. I think the idea of the asymmetric. The naming came from the fact that the public key is related to secret key, but it's not recoverable. So if you start sharing your asymmetric key, still you're doing asymmetric cryptography. You're not going to see. Yeah, I mean, the reality is that if the algorithm that you're using is use different entity to encrypt and decrypt, then it's asymmetric. If you use the same secret to decrypt, then it's symmetric crypto. Even, for example, I can encrypt my data on the cloud. Nobody else knows that secret. I haven't shared it with somebody else. But because I'm using the same secret to encrypt and decrypt to do the operation and reverse it, then it's a symmetric crypto.
Okay, thank you.
Sorry. Thank you very much for the attention. I can get that.